Hello, my name is Juliano Maloney. I'm the EMI EMC product manager here at Ansys, and today I'm going to present the EMI EMC workflows in HFSS presentation as part of the HFSS track in the Solutions Theater. I'd like to start this presentation showing some information with respect to the EMC lab test cost. For testing a prototype, a physical prototype, it's usually expensive. You need, of course, the product so you can run several tests on it. There are some pre-compliance tests that you can perform in-house. So if you have to change something on your design, usually you have to redesign your print circuit boards, you're going to need a new prototype, you have to assemble all the components, you have to redo all the tests. That takes some time, and the cost could go up to tens of thousands of dollars. If you need a radiated emission test, for example, you might need a semi-anechoic or anechoic chamber, and you need some of your staff to go over there and perform those tests, or you can of course hire third-party companies to do that. But if you need to change the product at that stage, including all the costs regarding the tests and the man hours involved, it could go up to hundreds of dollars, hundreds of thousands of dollars. And of course, if you have a full platform like a vehicle, an airplane, and you go, for example, for a radiated immunity test, as we're seeing here on the right side, or even a lightning strike on an aircraft, and you have to change something on your prototype, if you sum up all of the cost, it could go up to millions of dollars. Just like in the lab, we do have some challenges on EMI EMC simulations. Here we have an example on the left side of a real EMC test. It's a bulk current injection test. And on the right side, we have pretty much the same test, but now in a virtual environment in HFSS. We run the same test, but now virtually. So you don't need a physical prototype. You need only information in your design and, of course, information on the environment, such as the BCI probe, the length of the cables, listens, and so on. Most of these details, they are described on the standards. So we do have in HFSS some 3D components and workflows that helps our users to set up these kind of tests. And of course, since we're talking about electromagnetic interference, that's the sum of signal integrity, power integrity, PCB, RF, antennas, cables, housing, connectors. So that makes the simulation process more complex. And that's one of the biggest challenges that we have in electromagnetic simulations for EMI EMC. But I'm going to show some technologies in HFSS that helps our users to overcome all of these challenges. Here we have an example of a laptop computer. And as you can see here, we have mechanical CAD, we have electrical CAD, we have antennas. And the first challenge that we have is how can we integrate all these information, since usually they come from different sources. We have a very nice platform in HFSS called HFSS 3D Layout, where we can import both mechanical CADs, electrical CADs, and also we have a really good way to handle all this information. If you take a look at the print circuit board, that's a complex geometry, and if you try to rotate, perform some operations in those type of the geometries, that could be really tricky. And we do have some really good technology in HFSS 3D layout to handle all of that. The second challenge that we have is, of course, how can we mesh a complex geometry like this? HFSS, in order to solve Maxwell's equations, we have to mesh the geometry. And in HFSS, we do have very good meshing technology. Of course, the cornerstone of HFSS, it begins and ends with the automatic adaptive meshing refinement. So every HFSS simulation, it's really accurate. We can see here on the left side the adapted mesh for this print circuit board and the mechanical CAD only on the down part of this laptop, but you can see that the mesh is not uniform. HFSS refines the mesh to get a better accuracy, not only for the geometry, to represent the geometry, but also to really represent the electromagnetic field behavior. We also have dynamic surface resolution operations for complex CAD geometry. So if you have curvilinear, spherical geometries, we apply dynamic surface resolutions to each part of the geometry, which speeds up and enables a very good mesh. And we have a flex meshing algorithm that is really good for extremely complex structures, just like the one we are seeing here. But we can use electromagnetic simulations in all of the stage during the development of any given product. And of course, there are benefits, and some of the simulations require more effort. So when you are designing your product, you have to improve your design using simulations. That's the best time to use simulation, because simulation doesn't require too much information at that stage, and you can get a lot of benefits. That's the left part of the curve. So for example, we have here a back drilling via animation, but we can optimize transitions, we can optimize PCB layout, we can optimize many things in your design that's going to solve signal integrity problems, power integrity problems, and also EMI problems. And then of course you can simulate your full product. In this example, we're still talking about the same handheld computer. If you simulate a full product, you can see more output, I would say, for the electromagnetic simulation. You can see interference between antennas and digital signals, the sensing. You can see crosstalk, radiated emissions from your product, and you have some benefits by doing that, because you are using electromagnetic simulations to simulate your whole product. So radiated emissions, for example, is another thing that you can get as an output for that. But then in the end, what most users would want is a virtual compliance. Is my computer again is going to pass or fail a given FCC, IC, ISO, or CISPR standard? So we can do that, of course, but then you're going to need way more information, especially if you take a look in here. We have a semi-anechoic chamber, we have an antenna, so we're going to need antenna factor, we have turntables. So if you do your design really well, improving your design here on the left side, and you can perform your full product simulation, you will likely won't have any problems during a compliance test. But we do have technologies and workflows that helps our users to go through all these stages. So let's talk about the first stage, that will be improving the design itself. Here we have some animations that shows some of the things that we can do with HFSS. On the left side, we have a back drilling via. That's a process where we back drill the via to remove the stub. So in this particular case, we can see here the electric field and the back drilling via. And as we perform the back drilling, we will see that we have a much better improvement both on the TDR and insertion loss, and of course on the eye diagram. So we can use HFSS to evaluate all of that, including manufacturing tolerances. On the right side, we have a 10 gigabits signal that goes from that package on the bond wire, goes to the PCB and vias. And as you can see here, we're running a design of experiment. We're changing now the radius of a via, but we can change the radius of the bond wire. We can change the layout of a given net, like what we are seeing here now with the variable called D1 that controls that net. And we can evaluate the best design, so we can have a much wider open eye for this signal. Another improvement that can be made is an example for a book current injection. We have a 12 volts DC that comes from that red cable on the right, and we should have ideally 12 volts DC on that component called U1. But that's not happening in reality, and in this book current injection test, we're injecting a 300 megahertz continuous wave in here. So usually we do in this particular case, we add capacitors to try to filter that noise. And we can see here on the right side, if we change the position in this particular case of capacitor 1, how the noise that is going to be generated or injected by that BCI probe is suppressed and reaches the U1 component. We have in blue the 12 volt DC flat that it's on the other end of the cable, and you can see here that we can change both the values and the position of this capacitor, and we can see how much of that noise can be suppressed. And HFSS leverages high performance computer technology, so all of these variations, they can be solved in parallel, and they're really fast. We can end up with design of experiment response surface, just like what we see here on the right side. So we can change the capacitor 1 position both on Y and X axis, and we can see the best values for both capacitors C1 and C2 that will suppress that noise. And now let's talk about the full product simulation. We're still talking about that laptop, and of course after you can improve vias, back drilling vias, the length, the width of the vias, we can simulate the whole product, and we can see really good benefits by doing that. You can see radiated emissions, for example, from your device under test. You can perform some RFII simulations. You can see crosstalk. You can see, if you have some digital signals, desensing the radius of antennas that you have in your product. And of course, you can get a complete signal integrity and power integrity picture of your entire product. We have a very good example from our friends at Smart Modules. This is a full product simulation where we have again electro-CAD and mechanical CAD. So we have connectors, print circuit boards, and once you have optimized in your design, you can run a full product simulation, and then you can still change some of the routings. You can change the stack up, you can change the design of planes, and you can improve a lot your signal integrity and also EMI performance. In this particular case in here, we have two eye diagrams. The original design, revision A, you can see the eye diagram. Even though it's not overlapping the green mask, it's a little closed. So after improving your design a little bit, you can see now that the eye is much open now, is on revision B, and that's one of the good things that you can do with simulation. You can not only see if your design will attend a given eye mask or a specific standard, but you can also improve that because there are several manufacturing tolerances and another tolerance that you need to account for in here. So if you optimize your design even better, you likely have less problem in the field. And of course, what most of our customers are looking for is virtual compliance. They want to know if your product is going to fail or pass any given standard. And for that, as we're showing, if you improve your design, you likely have no surprises and no issues during the compliance test. But then we do have in HFSS several technologies that helps our users to simulate that. So in this particular case, we have a CISPR 22 setup here with a semi-anechoic chamber, antennas, and we have again our laptop that we are using as an example. And we do have in HFSS really good technologies that provide us a very good and streamlined workflow to simulate those kind of problems. We have 3D components. For example, for entire chambers, we have 3D components for electrostatic discharge, radiated emissions, bulk current injections, all of that. It comes with HFSS installed, and they follow some of the standards. And of course, we do have some technology that I'm going to highlight in some slides that helps to solve those electrically large problems. In this particular case, we have the laptop now in a turntable, and as you can see in here, we have an anechoic chamber with absorbing elements, the antennas, so we are using the antenna factor in here. Of course, there are some simplifications or assumptions that we can do in HFSS where we don't actually need to simulate the absorbent elements. For example, not even the antenna. We can calculate electric field anywhere in space, even outside the simulation domain. But if you want to follow the standards and get some really close results compared to what you're doing in the lab, then we do provide those 3D components for specific standards here in HFSS. For example, we have bulk current injection, not only the test bench model, but we also have some BCI probes as an example, as 3D components. We have radiated emissions according to CISPR 25, just as well as conducted emissions test bench models. We have electrostatic discharge models. And since we're talking about EMI EMC and all the complexity, we need some really good technology, and HFSS provides exclusively technology that helps our users to solve extremely complex EMI EMC models. Here we have an example of a radiated immunity test from one of our partners. It is published on Ansys Advantage. So you see here an antenna that is generating noise, and you have to first measure electric field inside your vehicle, and then you have to make sure all the electronics components will behave as expected. In this particular case, in here on the left side, we're simulating the full chamber and the antenna. But we can use some hybrid technologies like FEB, finite element boundary integral, where we can eliminate all the air volume around the antenna and the vehicle. So what we see here on the right side on the top is a horn antenna where we have the simulation domain around that antenna, and then we have the chassis of the car, and again we have an air box, a conformal air box around that chassis, and there is no air between those two separated domains, but they are fully coupled through the method of moment. So the finite element boundary integral is something that is widely used to simulate those electrically large models. On the bottom, we can see here we have a dipole antennas, and we have really conformal air box around the radiating elements, and we have again the car, the vehicle in this case, rotating, and all of that can be simulated in parallel, all the rotations. So if we leverage HPC, high performance computing, we can get really fast simulations using full wave technology in HFSS. If we need to simulate models that are extremely electrically large, which means that they are big in a physical size, and we need to simulate that at a very high frequency, we need to move from full wave to asymptotic techniques like this shooting bouncing rate plus. The greatest advantage of HFSS is that we can leverage shooting bounce rate technology, but we do have advanced physics models such as creeping waves, UTD, and PTD that improves the results and the accuracy of shooting bouncing rays. So the results can get closer to what you would expect in real life, and also, of course, close to full wave simulation results. Here in this particular case, we have on the top right side how the shooting bouncing ray works. So we have antennas, and we shoot rays from that antennas, and every time that ray hits a surface, we calculate the currents, and the ray bounces again to another surface where we again calculate the currents. So using this technology, we can see that we can simulate RF cosine examples for antennas in airplane, all the antennas in an airplane. Here again, we're leveraging shooting bouncing ray plus technology to simulate this entire environment. It's an industrial facility, and we have here a worker with a Wi-Fi receiver, and we have a microwave heater that is causing and generating some noise. So every time that this work gets closer to the microwave heater, you can see on the left side on the constellation diagram, we are using a 64 QAM modulation. The symbols, they scrambles. That's because of the interference generated by the microwave heater. We can also see on the interference matrix that we have interference between the microwave heater and the phone, and if you click on that, you see the EMI margin that we have at any given distance from that noise source, which is the microwave heater. We also have encrypted 3D components technology in HFSS, which means that any provider can give you a component for a capacitor, a connector, and an antenna, and they can protect their IP. So here on the left side, we have an HDMI connector, and we see the encrypted HDMI connector. So you can actually place that connector on your print circuit board, but you can't actually see what's inside. Since HFSS leverages automatic adaptive mesh refinement technology, we don't need to know what's inside of that connector, but HFSS generates a very accurate mesh. That's a good way for an integration between different suppliers and OEMs, integrators, to create full models and get a full picture. One EMI example that we can see here on the right side is a coupling between a differential clock and an antenna and a NAT that connects to the chip. If we don't consider the 3D component itself, we would consider only the coupling between the traces. But it's also important to account for the coupling between the traces and also the antenna. So we can see on the right side when that differential clock's on or off the Wi-Fi spectrum. So we can even see the channel that's interfering in that particular case. We also have in HFSS an advanced cable modeling solution. So when we are thinking about cables, a car, they have dozens of miles of cables, and if you take a look at the cross section of the cables, we have hundreds, maybe thousands of conductors in there. And if we try to simulate that using the rigorous finite element method, thousands of cables, that's something that's not practical. So in HFSS, we have a very good workflow where we solve the cross section of cables using a transmission line solver, and then we map the fields on the bundles in HFSS. So here on the right side, you see several wiring harness bundles. Those are red tubes, those red cylinders, and you can see the electric field around them generated by specific signals within that bundle. So we can simulate full vehicles in HFSS considering hundreds of conductors. And we also talk about the mix between RF, signal integrity, and also EMI. As we were talking about, EMI is always a combination of most of the electromagnetic coupling that we have in any given product. So in this particular example, we have a generic cell phone where we have two antennas, a Bluetooth antenna and a GSM antenna. And in this case, we have a package in the middle of the PCB, and we have a signal that goes from that package to the USB connector on the right side of this phone. As you can see in the middle of the screen, we have an eye diagram that shows that the eye is open and the Bluetooth and GSM antennas are off. As we turn on the antenna, we can run the same signal integrity analysis, but now you can see that there's a violation in the eye mask, and that's basically because of the interference from the antennas into that particular signal. So those are the type of simulations that requires both RF and signal integrity background, and in the end, it's an electromagnetic interference analysis. Now we have 5G. So with 5G, we have, instead of a single antenna, we have an antenna array. In this particular example, we are using again a generic cell phone and a much bigger array that you would find in a cell phone. You can find those arrays. This is an 8x8 array working at a 28 gigahertz that could work on could be placed on servers and big electronics. On cell phones, we actually have smaller arrays, but we created this mock-up just to show how can we run a 5G millimeter wave array antenna affecting digital signals in your print circuit board. So not only we have the array, but if you take a look at the print circuit board, we have a controller and a DDR4, and we have several nets that are connecting this memory module to the controller, and we will be evaluating a single signal in here just for the sake of clarity in this net called DQ7. One thing that we have on antenna arrays is that if we change the magnitude and phase of each antenna, we change the radiation pattern. So what we see here on the eye diagram is the DQ7 DDR4 signal. As you can see, as the antenna array, is focusing the radiation towards the sky, there's no interference on the eye diagram. But if we change that eye diagram, so the radiation now is focusing towards somehow the print circuit board, you can see the eye diagram now is really closed. So this is a new electromagnetic interference now that comes with 5G. So now that we have antenna arrays, we need to make sure that many, depending on the excitation of your antenna array, that your electronics are going to perform as expected. So the great advantage of using HFSS is that we can simulate finite arrays, we can include IBIS models, and we can run this type of simulation that combines finite arrays, signal integrity, everything in a full system. And with that, I would like to conclude my presentation just highlighting again some workflows that we had to integrate mechanical CAD and electro CAD in HFSS 3D layout. It's a really powerful environment where we can merge electro CAD, mechanical CAD, and simulate your whole product. We also offer EMI EMC 3D components, templates, workflows for especially full system virtual compliance, and cable modeling techniques to model several conductors in a platform. The meshing algorithm that we have in HFSS it's automatic and it adapts as needed. So we always have the right answer with HFSS. And now during the last years, we haven't improved the algorithm by adding some dynamic surface resolution operations to handle complex CAD, as well as flexible meshing algorithm for those complex assemblies. And of course, in HFSS, we have not only finite element methods in time domain and frequency domain, but we also saw how can we leverage Phoebe, finite element boundary integral, and also the hybridization with a shooting bounce rate to simulate electric large structures, just in the case of antennas close to airplanes and automobiles. And of course, we can use high performance computing to get those answers really, really fast. With that, I would like to thank you for your time, and please enjoy the rest of the conference. Thank you.